Hey, welcome to The Explainer. Today we are going to tackle one of the most, and I mean most, fundamental building blocks in all of electronics, the potential divider. Now, it sounds kind of technical, but trust me, this simple circuit is incredibly powerful. It's probably hiding inside a bunch of devices you use every single day. So let's get right into it.
So, picture this. You've got a 9-volt battery, right? But the little project you're working on, it needs exactly 3 volts, not 9. So, what do? Well, this is exactly the kind of problem a potential divider is built to solve. And honestly, the solution is way simpler than you'd probably guess.
Okay, so what is a potential divider, really? How does this thing let us just, grab the exact voltage we need?
Well, at its core, a potential divider is just what you see here. You've got a power source giving you some input voltage, we'll call that Vin, and then you have 2 resistors, R1 and R2, wired up one after the other in series. And here's the magic. That total voltage from the source gets shared, or, you guessed it, divided, right between those 2 resistors.
And that's basically the whole principle right there. It's a circuit that's designed to do one thing, and do it really, really well. Spit out an output voltage that's a precise fraction of whatever you put in. It is, by far, the simplest way to get a smaller, specific voltage from a bigger one.
Okay, but how does it actually work? Like, how does it know how much voltage to give each part? Well, it all boils down to one surprisingly simple formula.
And here it is, the magic formula. It looks a little mathy, but it's super straightforward. Your output voltage, Vout, is just your input voltage, Vn, times this little fraction here. The resistance of the second resistor, R2, divided by the total resistance of both resistors added together. That ratio, that is the secret sauce. You pick the right resistors, and you can get pretty much any slice of the input voltage you want.
If we break it down, it's really just a simple 3-step process. Okay, so first, you just add up the 2 resistances to get the total. Easy. Step 2, you figure out the ratio. What piece of that total pie belongs to the second resistor? And then, for step 3, you just multiply that ratio by your original input voltage. Boom, that's your Vout. Simple as that.
All right, let's try a real example to see how this plays out. Let's say our input voltage is 6 volts, and we've got a 1 kilo ohm resistor for R1 and a 3 kilo ohm resistor for R2. Okay, so first step, total resistance. 1 plus 3 is 4 kilo ohms. Got it. Now the ratio. R2 is 3, the total is 4, so our ratio is 3/4. Now just multiply that by our 6-volt input, and what do you get? Exactly 4.5 volts. See? It's perfectly predictable. Now, getting a fixed voltage is cool and all, but this is where potential dividers get really interesting. What if we could make them dynamic? What if they could actually sense the world around them?
So, what if one of those resistors wasn't just a fixed value? What if its resistance could actually change, say, based on how hot it is, or how bright the room is? If we swap out one of those plain old resistors for a special component, like a thermistor that reacts to heat, or maybe a light-dependent resistor, an LDR, that reacts to light, all of a sudden our simple circuit becomes a sensor.
So, check this out. In a circuit like this one, if that variable resistor is an LDR, well, as the light hitting it gets brighter or dimmer, its resistance changes. And because its resistance changes, its share of the total voltage also changes, which means Vout changes too. It's like our circuit can now see how bright the light is in the room.
Okay, time for a little interactive challenge for you, straight from some of the practice questions. Think about this for a second. Let's say we want our output voltage, the one across component Y, to go up when the light in the room gets brighter. So, where do we put the LDR? Do we put it at position X or at position Y? What do you think? And the correct setup is A. Let's break down why. The key thing to remember is that an LDR's resistance goes down as light gets brighter, okay? So, we want the voltage across Y to go up. For that to happen, Y needs to get a bigger slice of the voltage pie, and that happens when the other resistor, component X, gets a smaller slice. For X's voltage to drop, its resistance has to drop. So we need to put the LDR at position X. As it gets brighter, the LDR's resistance falls, leaving more voltage for our fixed resistor at Y. Makes sense, right?
This whole idea of a variable resistor, one that you can actually control, leads us directly to one of the most common and useful electronic components you'll ever find.
Say hello to the potentiometer. You can just think of it as a potential divider all wrapped up in one neat little package. It's got this sliding or rotating contact that lets you smoothly pick off any voltage you want, from 0 all the way up to the full input.
And I guarantee you've used one. Ever turned a volume knob or used a light dimmer switch? Yep, that's a potentiometer.
So on the screen, you can see how the physical knob connects to the circuit diagram we use. That little arrow in the symbol, that's the key part. We call it the wiper. It represents the moving contact that physically slides along a resistive track inside the component, letting you tap the voltage at any point along its path.
But these things are for way more than just volume knobs. In a science lab, they are absolutely essential for an ultra-precise measurement technique called the null method.
Now, I know this circuit looks a little intense, but the idea behind it is actually really clever. What we're doing here is using the potentiometer to compare the voltage of an unknown battery against a known stable voltage source. We're trying to measure its EMF, that's its electromotive force. You can just think of that as the battery's true raw voltage. And to do it, we have to find this perfect balance point.
So what is this balance point? Well, it's the one specific spot along the potentiometer wire where the voltage it's supplying perfectly matches and cancels out the voltage of the battery we're testing. And how do we know we've hit that magic spot? We use a super sensitive current meter called a galvanometer. When it reads zero current, nothing flowing, we call that a null deflection, and we know we're perfectly balanced.
And this is the really genius part of this whole technique. Right at that balance point, there is literally zero current being drawn from the battery you're testing. Now, why does that matter? Because it means we're measuring its true, unloaded electromotive force, its full EMF, without losing any voltage to the battery's own internal resistance. This is what makes the measurement so unbelievably accurate.
Let's actually see this in action with some numbers. Say we start with a known cell, cell A, and we know its EMF is 1.02 volts. We hook it up and find the balance point at 37.6 centimeters along the wire. Okay, great. Now we swap in our unknown battery, cell B. We slide the contact along and find its balance point at 55.3 centimeters. Now we can just use a simple ratio, and a quick calculation tells us the unknown EMF is 1.50 volts.
Pretty slick, right?
So it all comes down to this really simple and elegant relationship you see here. The ratio of the voltages of the two batteries is exactly the same as the ratio of their balancing lengths on the wire. Is this beautiful physical principle that lets you turn a simple measurement of length into a super precise measurement of voltage.
So think about where we've been. We started with a simple circuit of two resistors, and from there we got to sensors that can see light and even incredibly precise measurement tools. The potential divider is such a simple idea, but its applications are just so powerful. It's working right now in the sensor that automatically dims your phone screen. It's the volume knob on your speakers. It's the dashboard lights in your car. This simple principle of dividing voltage is quite literally everywhere. So, how many have you used just today?
Thanks for tuning in to The Explainer. We'll catch you on the next one.